Okay.
Alrighty, I'm going to go ahead and get started so we stay on time. Must be really good cookies out there because there's nobody in here yet. And I asked them for me to give my own introduction because the one they have is about 10 years old. So I'm Kristof, I'm from Marquette University. I'm an associate professor there. My background is in sports biomechanics, and the last couple of years I've fallen into a role that involves me working with our sports athletic teams on campus and sports science data analytics role. So I thought what I would do today is go through a couple of applications. We've worked with some teams and sports coaches, and specifically how we've applied some machine learning neural network type models in those situations. So before I get started, I always want to make sure I thank our lab group, past and present students in the biomechanics lab. We work pretty closely with the strength and conditioning staff, so their support is always appreciated. And then we have research support from our newly built Athletics and Human Performance Research Center on campus and our recent Masters in Sports and Exercise Analytics at Marquette University. We'll start with this little cartoon. This is your machine learning system. Yep, pour the data into this big pile of linear algebra and collect the answers on the other side. What if the answers are wrong? Just stir the pile and they start looking right. And so I think it's a pretty good depiction of a misconception that some people have, and of how we apply some of these newer algorithms. And so I think that's where hopefully some of the applications I'll go through, I'll take step by step through of how we apply some of these to get away from just stirring the pile. Another quote that I just recently saw, I thought was kind of telling of how we approach things at the moment, is that when we raise money in academia for positions, we say it's artificial intelligence. When we hire, it's machine learning, and when we do the work, it's logistic regression. So in all fairness, regression approaches, basic simple linear regressions or logistic regressions can probably do a lot of the work, but there are reasons why we've started to use some more complex models like neural networks. And so there's definitely a positive side to what we can gain from these models. And so here we have very simple, straightforward, feed-forward neural network. And so some of the things that we say that we gain from using these models is that we can model fairly complex problems. They function as universal function approximators. They're able to model interactions between variables, look at nonlinearities in data, as we use different transfer functions between input and output layers. We can also model time series data, which is of interest to us in biomechanics, where we analyze human movement data, time series data, the ability to work with wide data sets. So wide data sets mean we have a lot of variables, but maybe not necessarily a lot of data points, which kind of feeds into the second part, is that it's really until I started looking into these machine learning neural network algorithms, we didn't really talk a lot about generalizability of our model. So it's just basically we have a lot of data, we fit the data with a regression model, and that's it. That's kind of the results that we got from our research, and we write that up. And so the concern wasn't always about generalizability to samples. So the first applied problem, we call predicting physiological responses to training demands in soccer players. So as a background, both of our men's and women's soccer teams on campus collect external load data. So this is GPS data or IMU data, where each player is instrumented with an inertial measurement unit during each practice and each game. So that means that we have gyroscope data, accelerometer, or magnetometer data. We know how fast they're running, how far they're running, how much distance they cover at a certain speed. And at the same time, there's also internal load, or physiological responses to exercise that are being collected. One would be an RPE scale, just simple on a scale of 0 to 10, how hard did you perceive that workout to be. We also have heart rate data, so it's more subjective measures of internal load. And so the reason that this is being done is that it's recognized that monitoring internal and external loads, right, is a way to manage performance of players from practices to games. So the problem, what we would like to do is we would like to keep track of how these things change and hopefully use it in the program design process of designing certain workouts where we choose a combination of external load variables that give us a certain physiological outcome to keep players in shape or to make sure that they maintain a basic fitness level. So for this problem, we wanted to model the association between external and internal load variables, first of all. And then we also wanted to determine the relative importance of each external load variable. So is it high-speed running distance? Is it how much volume they do overall in practice, the intensity of practice, and so on. So we monitored data we monitored 10 players for 2 weeks. Some of the external load parameters that we get from the player tracking software are things like player load. Think of this as an activity count from the accelerometer. So every time I perform a movement, it goes tick, you just moved, and it quantifies the overall amount of physical activity that the player performed. We look at high player load, above 80% of maximum, so this is kind of a measure of intensity, high speed running distance, and then the strength and conditioning coach was also interested in the mediating influence of somebody's fitness level, right? So how fit somebody is probably determines how they pursue a certain workload in response to a workout. And then we have our internal load parameters, RPE scale 0 to 10, and then the duration of time that their heart rate was above 80% of maximum. Should say that heart rate was only available for male players. And so our basic feed-forward network model, we just had an input layer with these 5 external load parameters, and we're trying to model or map these input variables onto these onto those outputs. Something that we also did here is we were interested in what's the relative importance of each of these inputs with respect to predicting these outputs. So we used a connection weights algorithm where we basically try to establish how much does each of these neurons turn on the neuron in the hidden layer, and then we map the relationship as these connections as a percentage of all the connections to give us an idea of the relative importance. Something that I want to talk about real briefly is this idea of overfitting, right? Which is, I call it's kind of the bane of generalizability, right, that we deal with in neural network modeling. And right, if we have our data spread here shown in the blue lines, underfitting the data will be a model that does not perform very well at all. We'll have large errors. What we desire is some sort of what's the word? A balance or a parsimonious model that gives us an overall pretty good fit, but that doesn't fit the data so well that it only represents the data itself, or that can generalize to a new population. And probably the best representation that I've seen of this is I can come up with a very good bed that fits exactly your data, right? Your outline, but it doesn't work for anybody else. So the generalizability of this model is very, very poor in terms of generalizing to other populations. So something that we try to deal with is, especially if we don't have quite that much data, we want to make sure that it still generalizes to new players, new situations. So we typically divide our data into training, validation, and testing sets. And what this looks like is that when we train the network, right, to model the association between our input and output variables, we have we have an error, which is depicted on the vertical axis here, and the iteration of trying to solve for the solution to the network on the horizontal axis. So as we go through a number of iterations, the error for a training set, which is about 70% of our data, typically starts dropping over time, right? We improve performance. We withhold about 15 to 30% of the data for validation and for testing. And we basically keep training the network, but at the same time as this training occurs, each time we test the network to make sure that the error also keeps dropping, which will, we can reach this asymptote here where the error didn't continue to drop, and we basically stop training when the validation error starts increasing again. So this is, again, a way for us to say, once the network performs better and better, we're coming up with that bed for that person, right, for that data set, but it's not able to generalize to new data. And then we can perform basic statistics, looking at correlation coefficients or shared variance for each of these, the training, validation, testing, and our entire data set. So some of the results, right? I think overall the networks that we came up with worked fairly well for the male. So we have our training, validation, and test R's with mean squared errors. And then if we look at the relative importance for males in explaining RPE, right, we can certainly see that there is high player load, so the intensity of the individual practices, and their fitness levels seem to moderate their perceived exertion response to each of the each of the workouts. If we look at their their quantitative physiological response, heart rate spent about 80%. It's more of a product of high-speed running distance. For female soccer players, the accuracy of the models was a little bit less, but again, we didn't have heart rate data, and so it wasn't as subjective. We're relying more on qualitative data. So the overall performance is a little bit less, and then also if we look at variable importance in explaining RPE, or their perception of the physiological response, also differed slightly from the males. And so we provided this data back to the strength and conditioning coaches and said that this might be a way that you can come up with workouts where you know which aspects of fitness levels that you're training. You could come up with workouts where you have high player load, right, high intensity, lots of high-speed running distance in order to elicit a certain physiological response. So in the future, we would like to make this a little bit more player-specific, where for each player we come up with relative importance scores. Perhaps we would also like to look into this model a little bit further and look at the predictive versus actual responses. So second example is using machine learning to model the relationship between volume load of training in relation to vertical jump performance. So our strength and conditioning coaches collect jumping measures pretty much on a weekly basis, and they use this as a way to monitor muscular power of athletes. And what our coaches were particularly interested in, they wanted to know how resistance training volume, so how much weight do they lift in practice and each of their conditioning practices, how does that influence the changes in volume or changes in muscular power if we take muscular power as a surrogate measure for readiness, right? So we're interested in, again, modeling the association between weekly volume load over time and changes in counter movement jump performance from the beginning of a program to the end of a program. And we were, again, interested in what is the relative importance of each week. So is there a certain week where there's a high volume load, a high workout intensity that might determine the outcome at the end of the training program? So we had 21 male track and field athletes that we used data from. They were monitored over 15 weeks of training. This is kind of their general outline for the resistance training program. And so I think this guy's in the way, but basically we measured counter movement jump height weekly, but only looked at counter movement jump height during week 1 and week 15, and just calculated a change score in terms of how much did they improve. So the model that we came up with, or that we used here, is we have basically 15 input parameters with the volume load of each week. We try to map that onto just a single change in counter movement jump performance. So here, again, we have data from 21 athletes. They're randomly divided into a training group. Training in this sense being training the weights of the network. We use 4 to validate the performance, and then we tested the network on 4 separate players. And overall, the R squareds are fairly high, so we feel like we did a pretty good job of modeling the effect of the relationship between volume load and the overall change in jumping performance. We can see here is that from the 95% confidence interval, the root mean squares, that for the test subjects, we were able to predict changes in counter movement jump height to within 0.21 to 1.47 centimeters. out of a total change in jump height of about 5 centimeters over the course of the 15 weeks of training. And then if we look at the contribution of each of the individual weeks, this is actually where probably the most interesting insight came from, in that in the black line here, over time we have the volume load. So this is the total tonnage lifted by the athletes during each of the weeks of resistance training. And we see this very stereotypical periodized up and down pattern that coaches will often talk about. If we look at the relative importance in gray, right, determining the change in jump performance, we have the greatest relative importance of these weeks where the volume load was dropped. Right? So this provided the coach with some insight, is that it's not always the weeks where you're getting after in the weight room, lifting a lot of weight, but those back off weeks, so these tapering weeks, actually seem to have a much bigger bearing on the outcome than some of the weeks where we have very high volume loads. So we would like to go with this, ideally in the future, instead of just predicting jumping performance, which might only be important for several sports, is to actually try to predict sports performance. The problem is that in track and field, right, we have all sorts of different measures of performance, and so do we z-score those? Do we create t-scores? How do we look? Right, just a lot of different options that we're trying to consider in terms of how do we actually quantify performance so that we have enough data to run these models. And then with that also to include more predictors. So here what we have is a training macrocycle. So this is a yearly training plan for athletes where we have different preparation periods, we have our competition period, and then of course as we go through each of these periods we have different combinations of general strength training, sport-specific strength such as horizontal jumps or vertical jumps. We do some speed training and other training such as working on aerobic capacity and flexibility, and so trying to see how those variables affect the performance of these models would also be of interest. Okay, application 3, predicting net joint moments during the weightlifting exercise with a neural network model. So here I have a stick figure of one of my favorite exercises of all time, right? So this is during the sport of weightlifting. So I'm not talking about going to the gym and doing bicep curls, lifting weights. There's the Olympic sport of weightlifting, the clean and the snatch, where this first phase is called the pulling phase, and we have this very stereotypical pattern of muscle involvement of the lower extremities, or extensor muscles and flexor muscles. And if we want to gain insight into how we control that performance, we really need an insight into the joint kinetics in terms of, are the muscles active concentrically, eccentrically, what is going on at the joint level. And the problem is that this relies on really resource-intensive data collections, expensive equipment, and is somewhat obstructive to the athlete because it typically relies on motion capture data. So we have to put markers on the person. We need force plates, and again, motion capture cameras. And so what we wanted to try to model is, well, we wanted to see if we could predict these net joint moments, or joint kinetics, from very simple measures of just something like a bar path. Right, so bar path, it's basically the movement of the barbell during the pull or during the snatch in this case. And this is something that you can do now with an iPhone. There's an app that uses machine vision algorithms that basically tracks an object and then automatically calculates the movement of the bar. So what we did, we tracked the vertical and horizontal position of the barbell, disassociated that into horizontal position, vertical position. Excuse me. Fed that into this feed-forward layer. We collected biomechanics data at the same time, so we have our outputs, and we're just trying to see how did these inputs map onto these outputs. And something that, since we're dealing with time series data here, we actually used feedback delays, so quasi-recurrent neural network models where as we're predicting these outputs, we kind of have an idea of what the outputs should be, so we use this data to kind of feedback and refine the training process of the weights within the hidden layer. And here, so weightlifters are pretty hard to come by at very high caliber. So what we did is we use K-fold cross-validation method, where basically what you see here is that we had a sample of 7 lifters, right? And we went through the 7-fold cross-validation, where what you see each time here is that the dark gray line is the ensemble average of 6 players that were used to train the network. This is the deviation, is the shaded gray area, and then the black line is the one person that was used to test the network. And so we did that, right, randomly went through and did this for each of the 7 athletes, or each of the 7 weightlifters. So here are our outputs in terms of predicting the net joint moments. So each one of these columns is data from an athlete. We have on the top hip net joint moments, knee net joint moments, and then ankle plantar flexion moments. Again, for the most part, you can see that they're pretty good fits. Right? We saw that for the ankle, we were able to definitely predict ankle plantar flexion fairly well. For some of the other joints, such as the hip joint, sometimes we have a little bit of overestimation or underestimation of the net joint moments. If we look at the percent difference between some of these variables, they tended to be on the larger side of what we would perhaps deem usable for maybe biofeedback, but the overall pattern seemed to match well. And this is up to debate if we talk to coaches, whether is it just the peak magnitudes that matter, or is it really the patterning, the dynamic timing of the moments that is more important for performance. Okay, and then our last application, we're looking at ground reaction forces during runners, or during running for long distance cross-country runners. So we know from the sports medicine literature that excessive ground reaction forces are linked to running-related injuries. Shin splints are fairly common, or medial tibial stress in runners. And again, the assessment of running kinetics typically requires pretty expensive equipment, such as either force plates or instrumented treadmills, where we basically trace the ground reaction forces, so the forces between the foot and the ground. And either doing this inside the lab or running on a treadmill might not be ideal. So what we thought is like, well, maybe we can come up with a model to predict ground reaction forces from something like wearable technology with an IMU affixed to either the pelvis or maybe the tibia. And we're interested in also looking at different foot strike patterns and ideally doing this across a range of running speeds. So I had a student that took on this project, and one of his interests was not just coming up with a model, but really coming up with a really robust model. And so what he did is he actually went through a bunch of configurations of using two hidden layers inside the neural network, and then also running this for different error goals. These error goals were derived from looking at the smallest worthwhile change. If we look at the statistics based on what is suggested in the literature, so the smallest worthwhile change that was suggested was 558 newtons, and then we also looked at half of that. And so this is kind of what this looks like, where we have our input is the accelerometer data from the tibia, so just attached to your shank essentially, feeding that into our two hidden layers, and we're trying to predict vertical ground reaction forces. Did this for about 30 some runners at different running speeds, different foot strike patterns, and we withheld data from 2 females and 2 males with different foot strike patterns, and at 3 different running speeds that we then used to test the network. And so one of the things that we found is that using 10 hidden nodes in the first and second layer and a training goal of the smallest worthwhile change divided by half gave us an acceptably low error. And then over here are kind of the mappings of in the dotted, let's go, the dashed pink line is the accelerometer data. So that's the input that we acquire from the accelerometer, so from our wearable technology, kind of our field-based approach. The dotted blue line are the measured ground reaction forces in the lab on a treadmill, and then the red line, right, is the prediction that we get from the network. I should say that the speeds here are, we have long slow distance speed, long slow distance but 15% faster, and long slow distance 30% faster. So long slow distance speed is the speed where most runners will spend their most mileage training. So if they're at risk for injury, it's probably going to be the speed where they log their most miles. So that's why we chose the LSD speed here. And again, correlations between actual and predicted ground reaction forces were fairly high. And then the average difference between actual and predicted ground reaction forces were also within what's been reported in the literature. So again, future directions here, I mean, the wearable technology market is booming, right? So we're trying to think of other ways to apply, to integrate this with other wearable technology. Okay, so again, one of my other favorite quotes when it comes to machine learning by one of my favorite authors, real stupidity beats artificial intelligence every time. So this is my way of saying, if you guys have comments on my stupidity dealing with this data, your time is now. So thank you. Questions?
So in your application number 2, where you were showing the graph like 15 weeks at a time and weeks where the weights were dropped,
Yeah.
you had the bigger influence on the improvement in the jump, or the biggest impact, right, on the jump. I wasn't sure if it's the reduction or improvement.
So I had so from before to after looking at positive changes in jump height, right? And so they had the greatest relative importance of increasing jump height.
And was it how much the reduction was, or what?
It was just the absolute number. So we didn't look, so I don't know if you're asking us if we calculated the percent reduction. I mean, the inputs were just the absolute volume load numbers. So week 1 you lifted 100 tons, and that, right, week 2, 200 tons, and then during the back half week it was 50. So I would say it's the absolute numbers. We didn't look at the relative reduction to what came before.
So in that 3rd week, if you dropped it to 60 instead of 50, you're saying that would have improved your jump length?
Not quite. I don't think I could go there. Right? We say that overall the reduction, the weeks where there was a reduction in volume load seemed to have a large impact on the change in jump performance. Right? I don't think we haven't tried to quantify what it is specifically, like what the numbers would be. Or by how much you would need to reduce it to see the biggest impact, the biggest change.
Are you guys monitoring the athletes only during practice or weightlifting? Training periods?
So I know, so our strength and conditioning staff, right, they collect more data than this. So some of the athletes wear sleep monitors. So there are other data that are being collected.
But not during games at all? Can't.
So in the NCAA, they can wear player tracking technology. So So men's and women's basketball, men's and women's soccer, and I believe men's and women's lacrosse all wear the player tracking technology during games and practices.
Do they feel the, how do I word this, like, do they feel like they're being monitored and assessed at all times, or is it kind of like shielded from all the information, and they know about the information and like how it's being analyzed and stuff? I'm just curious because like there's an element of sport now that I think players probably feel like lab rats a little bit.
Yes, I can see what they do, and so we work pretty closely. So I share an office with the strength and conditioning staff, so we work pretty closely in terms of being as transparent as we can of how the data gets used. The coaches will try to use the data to inform what they do, and they definitely communicate that to the athletes.
And they're receptive to it?
Yeah, I think it takes a little bit of time to get some buy-in, but in the end, right, if you're monitoring, and with the workload monitoring, I think the biggest thing is the simplest explanation, I think, is during a game, right, your activity profile is this. So in practice, I need to make sure that you're performing up to those levels. Otherwise, when you get to a game, you haven't done your sprint work, you haven't done as many jumps, you're not going to be in good enough shape. And so I think that's probably the easiest way to communicate that. I think most student athletes will be like, oh, all right, that makes sense.
Yeah, I wonder if there's just going to be a change in the mentality of an athlete as this becomes, I mean, they're probably going to start younger and younger, and they're just going to grow up with this kind of, so they get buy-in just automatically. But I mean, I know Cal Ripken used to drink a 6-pack of beers after every single game and run on the treadmill for an hour, so obviously the different type of athlete now. And then, have you guys done any thought or work with like some of the Asian countries? Like I know Korea and Japan, they like practice crazy. Like I know the Korean basketball teams, they like 3 practices a day, before the season, stuff like that. And
so I mean, we haven't explicitly. But what I've heard from other coaches or other sports scientists is that even if they don't, right, the player tracking is just sometimes almost like just a good coaching education tool. When you go to the coaches and say, look, you ran your players into the ground, right? Their player loads were this high. Today they come in and it's only this, right? It might be because of...
Yeah, but their skill might be better, their skill level, shooting or whatever, because of so much practice, but yeah, the load is probably way too much. So.
Yeah, I think the load is where you risk, you'd be at risk of injury perhaps, right?
I need to interrupt, but we have 5 minutes to turn over the room for the next presenter. So if you'd like to have your questions out in the hallway, I'd appreciate it very much. Thank you.
I was looking at your slides, I'm looking at that right now. That you don't do that right now. Undergrad is, so I